Today we're learning about solving titrations for pH at various points in the titration when there's a weak acid or a weak base. So we've been using titrations ever since chapter 4. We haven't really seen them recently, but it's an acid-base reaction. Remember with the burette, and you're adding acid to a base or vice versa, and then at the point where the moles of acid are equal to the moles of base, you call it equivalence point, and you're trying to find that and solve for a concentration. Well, we now have the tools with the ice table to figure out the concentrations even if it's a weak acid or base. These are a little bit tricky just because sometimes there's more than one weak acid or base in the mix. So, example, 25 milliliters of 0.1 molar acetic acid. That's the Ka value, which is helpful to memorize for acetic acid. Titrated with 0.1 molar sodium hydroxide. What are the ion concentrations when 10 milliliters of sodium hydroxide are added? So, our sodium hydroxide is going to react with the acetic acid. So it's a stoichiometry problem to start with, and then it becomes a pH problem. So the steps to doing these problems: titration with a weak acid or weak base. First, do the stoichiometry, figure out what's left in the solution after the reaction, then figure out of the stuff that's left what affects pH the most, and finally solve for your pH. So we can do milliliters times molarity and find millimoles and then do a mole ratio with our balanced chemical equation. It is easier in these problems because it lets you see everything at once, and you can do all the problems the same to use an ICF table, very similar to an ICE table. First, you write the equation for what happened. I wrote HA. A represents the acetate ion. And then my lines are initial moles, because we're doing stoichiometry, so not concentration, change in the number of moles, and the final amount of moles. So we're going to do it like an ice table, but it's moles, not concentration. It's stoichiometry, not equilibrium. So start with the change line, just like in an ice table. Go back to the initial line. So I have my acid information. So volume times molarity is moles. So I have 2.5 millimoles for my acetic acid. Do the same thing with my hydroxide here and here. So I have 1.0 millimoles for hydroxide. And since it's not mentioned in the problem, that means we have nothing of the products and water, pure substance. We're not going to worry about it. It's not going to affect the pH. Okay, for the change, we don't need to call it X because we know how much is going to react. It's a limiting reactant problem. The limiting reactant in this case is the hydroxide because it's a 1-to-1 mole ratio, and we have more than 1-to-1 ratio of this one, less of this one. If it was perfect, it would be 2.5, 2.5. Hydroxide is only 1 millimole. That means that will run out first. That means all of that is used up, so that means the change is going to be minus 1. So we can fill in that line now. In the parentheses will be 1 for everything. Inside the parentheses is always the same thing. Our coefficients will be taken care of in the pluses or minuses at the beginning here. Okay, and then the final is just adding the first two lines. We have 1.5, 0, and 1 of that. That's the first step. Stoichiometry, figure out what's left after the reaction. We have some acetic acid and some acetate. That's important because both of those affect the pH. So step 2, what affects the pH? Both the weak acid, acetic acid, and the weak base, acetate. This is the conjugate base of acetic acid, so it's a stronger base than water. Stronger, it's still a weak base, but it's stronger than water. Okay, finally we'll find the pH. For a weak acid or a weak base or both, use the ice table. So there's my equation again. Ice table. This is what we're interested in finding from an ice table, the H plus concentration, because then we can find pH. Now you start with a change line. Initials in an ice table, you have to use concentrations. So I'm going to do my millimoles from my ICF table, stoichiometry, but you got to divide by the total volume, the 25 milliliters, and then we added 10. That's what those millimoles are in now, is the total volume. Okay, our change is going to be x, equilibrium, add up the two lines, and you can see that if we solve for x, we'll have the H plus concentration. So we're going to solve for x using our equilibrium expression. So products over reactants to their coefficients are equal to the Ka value in this case. When we solve for x, we get that x is equal to H plus concentration is 2.7 times 10 to the negative fifth molar. So then we can find the pH by taking the negative log of the H plus concentration. The pH is 4.57. When you get a pH, you should ask yourself, does this make sense? That it would be an acidic solution when I have not used up all of the acid that I started with? Yes, that makes sense. Next part of the problem, what is the pH when 25 milliliters of the 0.1 molar sodium hydroxide is added? So, first step, the stoichiometry, use the ICF table. Start with the change line. Initial line, the acetic acid is still from the previous problem the same. This time I'm using 25 milliliters of 0.1 molar sodium hydroxide, so that's 2.5 millimoles. And again, we're starting from scratch, so nothing of this has been made initially. Initially is where we're starting. Change line we can do because I can find the limiting reactant. The equation says 1 to 1 mole ratio. This one is 1 to 1 mole ratio, so limiting reactant is both of them. Both of them get used up because this is at the equivalence point when the moles of the acid are equal to the moles of the base. So our change is 2.5, same thing in each set of parentheses. Final, add them together is 0, 0, and 2.5. So step number 2, find the same main source of anything that can change the pH. So it's obviously going to be the weak base. So when you have a weak base, you find the pH by doing an ice table. Since it's a base, I'm going to write the reaction of the base acting like a base with water. So the acetate ion plus water turning into hydroxide and acetic acid. You actually could solve this with the same equation I used previously, the acid. As long as your equation has everything in it that you care about, it's fine. So we could do it that way, but it doesn't really quite make sense since this is just the base and not the acid in the base. So I'm going to stick with finding the pH of the base by using the equation for the base. So first the change line. Initial concentrations come from my ICF table, they come from the stoichiometry, but I've got to use concentrations in an ice table. So divide by the total volume, which is 50, not 25, 50. I had 25 and I added 25. And then my change is with x, equilibrium, add the two lines. So you can see that in this problem we're trying to solve for x again. X is equal to hydroxide concentration, which we can find pH from. So I'm going to solve for x using Kb. Problem didn't give me Kb. I know Ka times Kb is Kw, so that means Kb is Kw over Ka. Ka is given to me in the problem, and also you should memorize 1.8 times 10 to the 5th. Kw, you should memorize is 10 to the 14th. And that is all equal to x squared, the products raised to the coefficients, over this, concentration minus x. When you solve for x, you find out it's 5.3 times 10 to the 6th molar, and be careful that you know what that is. It's hydroxide. So you cannot just take negative log and call it pH because it's hydroxide. That's hydroxide. So there's a couple of ways to find pH when you have hydroxide. I'll do it one way in this problem and a different way in the next problem. So since I know hydroxide concentration, one way is that I know that hydroxide times hydronium is equal to 10 to the 14th. So I can solve for H plus by saying 10 to the 14th divided by hydroxide. Hydronium is 10 to the 14th divided by hydroxide. So that gives me Hydronium is 1.9 times 10 to the ninth molar. And then I can find the pH by taking the negative log of that, and you get 8.7. You gotta think, does this make sense? Well, I'm at the equivalence point, but I still have a weak base. I've made some weak base at the equivalence point, so the pH should not be 7, unless you're doing a strong acid, strong base. Yet since I'm making a weak base, it should be basic, and yes, 8.7 is basic. Okay, last problem for today. After the equivalence point. So, in this problem, 35 milliliters of sodium hydroxide is added. First step, stoichiometry. Figure out what's in your solution. So I'm going to do it with the ICF table and with moles. So initially, my acetic acid is still 2.5. I would go ahead and fill in the change line first, and then acetic acid is still 2.5 millimoles. Hydroxide is from my 35 milliliters, so it's 3.5 millimoles. And I can figure out the change because I can see the limiting reactant. In this problem, it's a 1-to-1 mole ratio, so for 2.5 of these, I should have 2.5 of these. I have more than 2.5 of the hydroxide, so that's the excess reactant. Limiting reactant is acetic acid, so that means that all of it is used up, so the change is 2.5. So fill in your change line. Then final, add up the two lines. You can see that we have hydroxide and a weak base. So step 2, figure out what affects the pH. I have hydroxide and a weak base. Well, I have a significant amount of hydroxide there. So some of this is going to make hydroxide. All of this already is hydroxide. And since it's a weak base, very little is going to make hydroxide of the weak base. Usually they something like 3%, 5%, something like that for weak. So definitely my main source is hydroxide. When you have strong base basically with weak acid or vice versa, or in this case strong base, weak base, it's the strong one that's important. So I then can find my concentration of hydroxide by dividing by the total volume that it in. That's 1 millimole divided by the total volume, which is my 25 plus my 35 milliliters. So now, this is like we were in the previous problem up here. One way to solve it is to find H plus, using H plus times hydroxide is 10 to the 14th. Another way, which is really the same equation with logs, is using POH. If you have hydroxide, you can find POH by taking the negative log of it. So POH is negative log of the hydroxide concentration. And then it's easy to find pH because POH plus pH is 14, which is the same as equation that we used earlier. H plus times hydroxide is 10 to the 14th. pH plus POH is 14. Same equation, just with logs. So 14 minus POH is pH, so that's 12. Now, make sure this makes sense. You have a strong base left over in excess, so your pH should be basic. Yes, it is.